This is video number 1 for sections 2.1 and 2.2. The topic is scattergrams and linear models. In chapter 2, we're going to be looking at how linear relationships show up in real world examples. Let me give you kind of the flow we're going to follow. The idea in all of these problems is there will be two variables that we're interested in learning about. We're going to collect some data for those two variables and organize our results in a table. Then we're going to draw a graph of the data. That graph is called a scattergram. Then we'll hope to find a pattern in the data so that we can create what's called a model. And once we have the model, we can use it to help us understand our situation a little bit better. Now remember, chapters 1, 2, and 3 are all about linear relationships, so the only kind of model we'll be talking about in this chapter would be a linear model. All right, here's the scenario we'll look at in this first example. This is a problem where somebody is interested in looking at smoking habits in America over the last several years. And so here's some data that's been collected in a table. You've got some years in the first column, and then in the second column, the numbers represent the percentage of American adults who were smokers in those particular years. And of course, you can see just from glancing at the information, it looks like that percentage has gone down through the years. Well, we need to be very specific about what our variables represent in each of these problems. And so here's a very typical kind of statement you're going to have, these let statements. Let P be the percentage of American adults who smoke at time T years since 1970. P, the percentage of American adults who smoke. T, the number of years since 1970. Now letter A says, let's figure out which of these is the independent variable and which is the dependent variable. The hint basically gives it away. When they write these let statements, they always mention the dependent variable first. So in this problem, P is the dependent variable, and of course that means that T is the independent variable. That makes sense if someone said, hey, what percentage of Americans smoke? The answer would be, well, that depends on what year you're talking about. So P depends on the T. All right, moving down to the next part, it looks like the next thing we're supposed to do is adjust the data that we had to fit with these variable definitions. This is very common in these kind of problems. Sometimes the numbers in the original table don't match the variables. For example, in this first blank here, I am not going to write 1,970 because T doesn't stand for the year. T, as we saw earlier, stands for the number of years that it's been since 1970. So when I go down to my table, my new table, I'm not writing 1970 here. I'm filling in how many years has it been since 1970? Well, the year 1970, 0 years have passed. 1980, 10 years have passed. 1990, 20 years, and so on, 30 and 40. These are the correct values of T that we need to use in this problem. Look back up at the P definition. P stands for the percentage of American adults who smoke, and when I look at the original table, well, that's exactly what they gave me, the percentage who smoke. So those numbers don't need to be adjusted at all. I can simply fill those in. 37.4, 33.2, 25.3, 23.1, and 19.4. All right, our next step letter C is to draw a graph of this data. And that type of graph is called a scattergram. Now, it says in the directions here to do that on the calculator, and that's what I'm about to show you how to do. The calculator certainly isn't the only way you could draw a scattergram. You could just make yourself a set of axes and create some scale on it and plot the points by hand. The faster way, certainly, once you get the hang of it, is to use the calculator. All right, here's the calculator. Let's walk through the steps of how to create a scattergram on the calculator. And you can refer to those in step C on your handout. First thing I need to do is hit Stat. Stat is located right here. And then I need to choose Edit, which is the very first choice, so you can just hit Enter. If you have any numbers in these columns right now from some other use of the calculator, to clear those out, you would arrow up to the name of the list. L stands for list. Hit Clear and then Enter. And you can do that for any of the lists where there are numbers present. All right, now what I need to do is I need in these columns to enter in my data. In list 1, I'll put my X values, or in this case, T values. Those were 0, 10, 20, 30, and 40. And then I go over to the second list, use the arrow there, and put in the Y numbers for this problem, otherwise known as P numbers for us. Just get those right from the table. 37.4, 33.2, 25.3, 23.1, and 19.4. All right, the next thing I have to do is I have to turn on the plot of the calculator. And the place I need to go to is called Stat Plot. It's right up here in blue, which means to choose it, I need to hit the blue button. So the blue button followed by Stat Plot. And I'm going to choose Plot 1. You'll see that right now it's off. I need to turn it on. I can choose it by just hitting Enter. And notice that off right now is highlighted. All you need to do is hit Enter on the on, and now on will be highlighted. All right, lastly, we just need to get a good viewing window. Thankfully, the calculator has a built-in feature for this. Every time you do this, if you just go to the Zoom menu and then go down to choice 9, which is Zoom Stat, you can just hit a 9 on the calculator. That will create for you sort of the perfect picture of this data. And so we've just drawn our first scattergram. Well, this is a pretty good picture. Letter D on your handout says, let's try to make it better by adjusting the window. For example, there's so many tick markings over here, it's hard to see them all. At the bottom, I'm not even sure I'm really seeing the x-axis or the t-axis. Well, let's fix that. I can go to the window button. And remember, I'm in control of what I see. Now, in a real-life problem, I just want to think about what the numbers mean. X in this problem were those t values. Well, we didn't have any negative t values, so I think if I just start at 0, that should be fine. And the biggest t value I had, I think, was 40 years since 1970. Why don't I just go out to 50 to make it a nice round number? And then I don't want to count by ones. I'm going to count by tens. For the y's, well, that's our p numbers in this problem, the percentages. If I want to see all the axes, I better start at least at 0, so I'm going to change that smallest number to 0. The biggest percentage was something like 37. Again, how about I just go up to 50 so that I can make sure I see everything clearly, and once again, counting by tens, I think, would be a good way to go. All right, and then if we hit Graph, we will go back to our picture, and you can see there, now I can see both axes, and I can see that I'm counting 10, 20, 30, 40, 50 on the T, and 10, 20, 30, 40, 50 on the P. Question E asks, is there a linear pattern to this data? Now this isn't saying are all of the dots lying in a perfectly straight line. It's simply asking, roughly speaking, does it seem like a line might do a good job of summarizing the pattern? And sure enough, it seems like, yeah, a line somewhere through here would do a decent job at summarizing what's going on here. So we're going to say yes to letter E. Letter F asks us to quickly copy this picture down onto our paper, so let's go ahead and do that. So back on the paper, the first thing I need to do is maybe add a little bit of scale. We had counted by tens, so 10, 20, 30, 40, 50. I'll put a little 10 to remind myself. Same thing on the P axis, 10, 20, 30, 40, 50. Maybe it's a good idea to write a T and a P to label our axes. And then we'll just try to do the best we can to copy the picture from our calculator screen. You go ahead and do that too. Five dots in all that we should have. Letter F goes on to say, now let's draw in a linear model. Now here's what that means. You're going to pick two of the dots, and you're going to connect those dots with a line in such a way that the line does a decent job at describing the overall pattern. There are always good choices of the two dots to pick and bad choices. For example, a choice that's not very good would be the second and third dots. Because if you connect a line through those 2 points, you get something like this, and that just doesn't quite capture the overall pattern of the data. Another poor choice, I think, would be the third and fourth points. If you connected those dots, you'd get a line looking something like this. Again, it just looks a little too flat to cover the overall pattern. It looks to me like a good choice in this problem might be the first dot and the fourth dot, for example. There are other good choices. If I connect as best I can the first and the fourth dot, I get a line that looks something like this. And it seems to me, I know that this line doesn't go through all of the points, but it does at least come close to all of the points. It seems to do a good job at summarizing the pattern. So again, we picked the first dot and the fourth dot to connect. You might have decided to pick something a little bit different, and that's okay. We'll go ahead and continue this problem in the next video.